Hello everybody, thanks for coming to this tutorial about using BPF in cloud native environment. My name is Alban, I'm a co-founder and director at Kinvolk Labs. We do consulting and engineering around open source projects related to Linux and Kubernetes. And at Kinvolk Labs, we are a dedicated team focused on innovation in our open source projects, and although collaborating with other software company and upstream projects.
Hi, I'm Marga. I also work at Kinvolk. I'm an engineer in the Flatcar team. Flatcar is a container optimized OS, which can be used to run inside Kubernetes if you want. But I'm also interested in other things, so I joined Alban today for this workshop on BPF because I found BPF a very interesting tool for debugging applications. Thanks.
So I mentioned Kinvolk Labs before. At Kinvolk, we had built 100% open enterprise cloud native stack. It includes a Flatcar container Linux or Linux distro for containers, as Marga mentioned, and Locomotive or Kubernetes distro. But everything we do show in this talk is about things you can do with other Linux distribution and other Kubernetes distribution. So it's generic technology, it's not tied to that. Next slide.
Yeah, so this is a hands-on tutorial. It's a workshop where we want you to follow along and do the exercises, the demos that we will show on your computer. So we want you to please now clone this repo and get started if you haven't already. Hopefully you have done this already, but if you haven't, we will cross our fingers that everything works out of the box and then you can get ready. The workshop uses Minikube. You can also do these things with other Kubernetes distributions, but we've optimized everything so that everything works out of the box, or hopefully works out of the box. So we recommend that you follow along using the tools that we provided. For example, for Minikube, we are providing an image that already includes the kernel headers, because for using these tools, you need to have the kernel headers. So yeah, and then you have to install the rest of the tools. We will do this along with you, all the different steps, but we want you to do this on your computer. You can also do it on a VM. If you want to use a VM, there's a few caveats that you have to take into account, but you can do it on a VM. All right, so we will start with our first hands-on task, which is to get Minikube running, install it if you haven't installed it. And for that, I will share my screen. Okay, so we have already cloned the repo in this Cloud Native BPF workshop directory. Hopefully you have cloned it by now. And we will go into the Getting Started directory that has a startminikube.sh script. Let's have a quick look at the script to see what it does before executing stuff. It's usually a good idea to check what things do. So this script downloads Minikube, then verifies the hash sums, and then it will ask you for confirmation because it will delete any Minikube that you have running if you have it on your machine. And then there's two options. Either you pass this use driver none parameter, which is only if you're running on inside a virtual machine, or you don't, and then it runs with virtualization. Ideally, you want to run with virtualization. It's a better idea. But if you are running this inside a VM, you want to use the use driver none parameter. All right, we will now run this. Start Minikube. So this is now downloading the Minikube image that we prepared for you with the headers. And now it downloaded the image, and now it will start Minikube. And this can take a while. So while this is running, we will go back to the slides and go back to explain a little bit why we're here and why this workshop even is necessary. Someone asked for the git clone URL again, so I will go back quickly to the URL. This is the git clone URL. And one thing I wanted to mention on this slide was that we also have a Slack channel for this tutorial. The Slack channel is in the KubeCon Slack, is 2-KubeCon-tutorials-BPF. So in that channel, feel free to ask questions or like answer each other inside that Slack channel. All right, so while Minikube is installing, why are we even here? What's all this about? So this is about debugging applications, and in particular, debugging applications inside Kubernetes. Debugging in general is hard, but debugging inside Kubernetes is even harder because like everything is running somewhere and we don't know, the pods are communicating with each other, and how do we even figure out what's going on? The BPF tracing tools are really good to help us figure out what's going on, but the problem is that BPF tracing tools that already exist out there were thought to be run on a machine and investigate what's going on inside the machine. So the tools that we will demonstrate today, Inspector Gadget and kubectl trace, are plugging this gap of like, how do we run these super useful BPF tools inside Kubernetes or with Kubernetes. And to explain a little bit more about that, Alban will tell you more about BPF and how BPF works.
Thanks. So BPF stands for Berkeley Package Filter. Maybe you know about that if you attend this talk, but I will give a bit more context. It exists for quite a while. Initially, it was for TCP dump that was used to filter network traffic on a raw socket so that TCP dump can be performant and you can specify filters on to say I only want to get HTTP traffic, for example, or only DNS traffic, or arbitrary expression like that. And to make it performant, they use BPF to execute the filter actually inside the kernel. So instead of TCP dump getting all the network traffic in user space in the TCP dump process and then filtering there, instead of that, it creates a BPF filter, put it in the kernel, and the kernel will only wake up the TCP dump process only when it's necessary for the packets you want. That was the initial use case. Meanwhile, recently it developed to a lot of more use cases. There are use cases for networking where different socket filter, or you can do traffic shaping. Use case for security, where you can have a seccomp where to filter the system calls you want to do, or more recently on Linux security modules. And lastly, there are use cases for tracing. So that's more what we are focusing today, where we can use BPF programs to hook into trace points or kprobs or uprobs and so on. So I can explain a bit more into details what eBPF is, this extended version of BPF. So the workflow looks like that. At the beginning, you write a BPF program, usually in a language like C. You can compile that with C-Lang LLVM into your BPF bytecode. And then this BPF bytecode can be uploaded in the kernel with a BPF system call. And then the first thing the kernel will do, it will verify the BPF program to see if it is safe. What it means, it will make sure it's not possible for the BPF program to access any random memory in the kernel if it is not safe, or corrupt your data or anything. So it's not like kernel modules where it's dangerous. Using BPF program doesn't risk crashing your kernel. So this BPF system call will return a file descriptor that represents your BPF program. But so far, it doesn't do anything until this BPF program is attached to something in the kernel. It can be attached with kprobs to some kernel function or to on the network stack at different layer. And this BPF program can make use of BPF helper functions to execute some things outside of the closed sandbox. There is another concept called BPF maps. BPF maps are kind of like global variables that are accessible from your BPF program and accessible from user space applications. So that's a mechanism for BPF programs on your user space application to communicate together through these BPF maps. So there are varieties of tracing tools on Linux that use BPF. I listed some of them here on the left side. There is Bpftrace, which has a custom language to write your BPF programs. There are BCC tools. BCC is a really useful repository with a lot of examples how to use BPF. So that's a good starting point to learn BPF, to see the collection of tools and try to execute them or to read how it's done by reading the source. There are other tools like traceloop, we will talk about it today, and other one. But most of those tools are more designed to run on one computer. So it's not really cloud native with something you can do on the Kubernetes level. For that, there are tools like kubectl trace. That's a kubectl plugin you can use on Kubernetes, and internally it will use Bpftrace on the worker nodes. And there is inspector gadget that reuse tools from BCC, from traceloop, and so on, to be able to use those tools at the Kubernetes level as well.
Right. So now we will move on with the next hands-on task, which is installing Inspector Gadget. Hopefully your Minikube installation is done by now. And if you run into any problems, remember asking on the Slack channel. It's KubeCon Tutorials BPF, to KubeCon Tutorials BPF. A few people are already asking questions there. Remember to ask questions there. Okay, so the next hands-on thing that we will do is there's another script which is called get inspector gadget, which first checks that you have kubectl installed and that it's working, and then checks whether you have it already installed. Like you could already have inspector gadget on your machine, and so it doesn't do anything in that case. And then tries to install it with crew if you have crew installed, because that's the recommended way. But if you don't have crew installed, it downloads the latest release for you and installs it in the same path as kubectl is. So let's now execute that. In this machine, it was already installed, so it didn't do anything. But in your machine, it's probably now downloading and installing the gadget. But this is now just installing the plugin. And what we want to do is to now install a pod in our cluster. So first we will check that it actually works by running kubectl gadget help. And we get the help. We see that it has a bunch of subcommands that we can use. And we will show a few of those subcommands in this workshop. And now that we know that it's running, we need to deploy a gadget. So how do we deploy a gadget? There's this very handy kubectl gadget deploy command that we will first inspect before we run it. This generates a YAML that says all the different the service account, cluster, role binding, and daemon set that will need to be created to run our gadget pod in our cluster. So now we will actually apply it doing kubectl apply -f dash. Okay, so this created the 3 resources, and we can check. It's container creating, so it's creating. It will take a little bit until it's done with everything. We can check maybe now. Yeah, so now it's running. So we have the pod and it's deployed in our cluster. And we can maybe check the logs, kubectl logs, kube system, And then this is Kubernetes app gadget. And yeah, we see that it launched and everything was successful, which is great news. All right, so we have inspector gadget in our cluster. What can we do with it? Let's go back to the slides. The first gadget that we're going to look at is called Network Policy Advisor. It's the use case for this gadget is when you join a project and it turns out your project has a lot of pods, a lot of services, they talk to each other, they transmit data, but there's not network policy. So everything is open, and if something malicious was going on, there's like no security whatsoever. And this is a bad idea, and you want to deploy a network policy, but you have like no idea of the architecture, you're new to the project. So how do you even start thinking about this architecture? And if you care about this idea of like, it's not a good idea to start putting the security at the end, Alban actually has a talk later today, almost like right after this workshop, called Pod Security as an Afterthought, where he will cover these issues and more. And so this is the problem, and this is what network policy can help us with. And we will see what this means with an example. In particular, we will use an example that was generated by Google, which is a microservices demo with a bunch of different services for like an e-commerce site. So it has a database, it has checkout service, shipping service, like they are all dummy services, but it can help you, give you an idea of what a microservice application looks like in Kubernetes. And we will use this example to try out the Network Policy Advisor. All right, so with that, I will share my screen again. And we will change to the 01 directory. In this directory, we have a YAML file and a README. In the YAML file, there's a bunch of different things. So we can, for example, grep for the different kinds of resources that are there. We see that there's a bunch of deployment, a bunch of services. If we try to make sense out of this, it would take a long time. So instead of doing that, we are going to use the Network Policy Advisor. So we will do kubectl gadget network policy monitor, because we first put it in monitor mode. And then we will say namespaces, and this is important, it has to be plural, otherwise it doesn't work. And then we will output this into a file called networktrace.log. So we are starting a monitor in the demo namespace, and we are saving this in the networktrace.log file. Now I will split the screen, and in this other side of the screen, let's change again to this directory. I will actually start the deployment. So first I will create the namespace, create namespace demo, and then I will apply the YAML file. Okay, all these pods are now getting created. It will take a while for all the pods to get created. We will now see that it says container creating for most of them. We can check that our network trace.log should be getting input soon, but maybe not yet because all the containers are creating. But okay, it's getting input. This is good. Now we will let this run, and in the meantime, I'll stop sharing and go back to the slides, and I'll tell you a little more about what the Network Policy Advisor does. So first, these were the commands, and remember, they are all documented in the GitHub repo, so you can go to the GitHub repo to check them out and check a bit more explanations about them. And then this is a diagram of what's going on with Inspector Gadget. So Inspector Gadget is a kubectl plugin. So the first thing that happens when you type kubectl space gadget is that it turns into a kubectl-gadget, which is the executable. And it only talks to the Kubernetes API. It doesn't talk to the node where the pods are running. Everything it does through the Kubernetes API. So the first thing we did a little bit earlier was to deploy the gadget pod, and that was done through the Kubernetes API. And then we asked that gadget pod to install a BPF program. In this case, in the Network Policy Advisor case, it was the BPF program to monitor what was going on the network. And all of that is done through the Kubernetes API. Inside the node, our gadget pod is the one that talks to the kernel. It creates the BPF program necessary for whatever action we are asking of it. And then it feeds this program into the kernel. And Alban will later explain more about what's going on in that stage. But this is the basic idea of what's happening, of what happened right now when I type network policy monitor. All right. And this is the log that we are generating. I show a little bit of what the log was looking like when I started generating it. And it has basically two types of entries, accept and connect. And these are like the TCP actions of accept and connect. And it stores the IPs that were involved, the ports, the pods, and all this information. Of course, this log is very verbose and it has a lot of information, and it wouldn't be nice to parse it as a human. Like, it's hard to make sense of all of this information. So of course there's a subcommand that helps us make sense of this information. So the report subcommand will parse this log and generate a YAML file, which is a basic network policy file. It's not the idea that you just use this YAML file and deploy it in your cluster and forget about it. You should look at it and think if you want to add things or remove things. It's just a basis. But it's very helpful to have it, to not have to think of all these policies on your own. All right, so hopefully our pods have deployed by now, and we have we can generate the report. Let's stop this tail. And yeah, there's one that crash loops because the recommendation service crash loops because it requires like a service account, and we don't have any service accounts, but the others are all running. So with that, we can actually stop the monitor with Control-Z, and we can instead call the report. And for this, we will pass -- input and the file we generated, which was networktrace.log, and then redirect this to network policy.yaml. So this will generate a YAML file with the network policy. Let's close the other window. And we can now look at the YAML file. And this is going to be complex because the service is complex, but basically you can see that there's ingress and egress for each of the different services involved, and the labels that they match, the ports that are used, etc. So as I said, this is basically a basis of what you want to then customize for your actual service. All right, that was it for the network policy. And now Alban is going to show you a few more interesting gadgets.
Thank you. So now I will talk about traceloop, which is the next gadget using BPF that I will talk about. So to summarize, I have this sentence. It's about tracing calls in C groups using BPF on overwritable ring buffer. That sounds quite complicated, so I will go through that and show what it does. So the use case I want to show there is something similar to strace. So I really like to use strace as a developer to debug my applications, but when I use it on a Kubernetes level, strace has some problems. It can be slow. It means it's not possible to use it for all my pods in production all the time, because that will make everything too slow. And although sometimes I have the use case where I have some unexpected crashes, and then when something has crashed, it's too late to use strace because the process is not there anymore, the pod is not there anymore, so there is nothing to use strace on. So here comes the idea to use something like a flight recorder, so to use BPF to record the system calls used by applications. But instead of printing them all the time, I just store them in a ring buffer. So there will be a ring buffer for every pod that constantly record the events, and it uses an overwritable ring buffer. That means that when the buffer is full, it just overwrite the oldest events and so on. In this way, we can use that to debug later. So if I compare strace and traceloop, that's quite different. Strace uses the system called Bpftrace to be able to capture the data. Traceloop uses BPF and trace points. With strace, you can capture the data on one or several specific processes. And on traceloop, it's done to capture events at the level of C groups. On strace, it can be slow because for every event, it needs to have some context switch between the tracee and the tracer for every system calls. And traceloop doesn't work like that. It has a ring buffer that is only written, and so they're just copying something in memory without actually having any context switch between processes. But strace has good points too. It is synchronous and reliable. It cannot lose events. So when you see the logs from strace, you necessarily see everything. It doesn't forget a parameter or something. Traceloop works in an asynchronous way and can lose events in some case. But it's good enough to debug most of the case. Even though it's not, it doesn't guarantee that you get all the parameters, everything. So if I go into a bit more detail, traceloop, similar interface to strace, it gives information about system calls, but it uses BPF program on the trace point enter. That means that every time a system call is executed on your system from any process, it will execute this trace point and execute the BPF program. And the first thing this BPF program will do will check which container it is about. So it can, in this example, use cgroups to look at the cgroup ID to know which container it is, or it can either use the mon namespace ID. And then, depending on the container, it can redirect the execution to another BPF program, one for each different container that has been configured. And it will output the data about the system call into a ring buffer for each container. And this ring buffer is written and overwritten in loop, but it's never read unless the user explicitly asks for it. For example, if they want to debug the application, if it has crashed, for example. In this case, the data is retrieved by the daemon set where traceloop is running, and the user can see it with kubectl gadget traceloop. So now it's time for another hands-on task. I will share my screen again. Here it is. I will go back to the parent directory, to the traceloop directory. And here there is a README that you can read from GitHub, or I will run commands directly there. So we have this kubectl gadget traceloop command. What it does is Add some subcommand, and one of the subcommand is to list the trace that is recording. So I will do kubectl gadget traceloop list. And it's a bit like a kubectl. You need to specify -n default for by default is used this namespace, or #A to see all the namespaces. And here I see quite a lot of pods that Marga has executed in a previous example from the demo namespace. Let me go to the top. We can see that those trace is from a pod that was terminated 4 minutes ago, for example, for this one. But it is traceloop still have a record from them, so it is a ring buffer with the last system calls that can look at them to see what's happening. So I will take the trace ID here, and I will do a kubectl gadget traceloop show. Oops, like this. Kubectl gadget traceloop show. And here I get the last few system calls that were executed by this pod before it has been. So I can go a bit higher. You can see a lot of text commands and some other system calls from the Java process. Okay. The second thing I can show here is I will run its example. I have one pod that I will start. It is executing multiplication and then saving the result into this file and then attempting to read this file. But because there is a bug in that script, it might not work as expected. So let's see that. I'll copy paste this from GitHub. So here I get an error message. It cannot read that file. So in this case, I will use traceloop again to attempt to debug that and to retrieve the result. So gadget traceloop list. See that even if my pod has terminated, I still have the trace. So that's this multiplication pod that returns an error. I can even delete it. And when it's deleted, I still have the trace that remain here. And I can show this trace. So here it is. So maybe I can ask the audience to see something. Do you see what's happening here? Okay, so we will go through that. Here it says it's attempting to opening this file, but this file doesn't exist. And if I look a bit above, I should see another here on this line, but this is a different file. That's why when I write to this file, I try to read a different file. That's why it doesn't work. We can also see here this read system call on the write system call. That's the BC program that receives on a standard input the multiplication to perform and to write the answer. So in this case, the answer is 42. Okay, so everything that was here is in this GitHub repository. So if you did not have time to do everything, you can also do it yourself later. I will stop sharing my screen. Go to the next slide. So here there are the commands that are executed. kubectl gadget traceloop list, and then this one I don't show. If the pod is still running, you can actually although see the last system calls at the time. But if the pod has been destroyed, then the API server doesn't know about it anymore. But you have to use this show command to be able to see that. Okay. And there are more gadgets in Inspector Gadget, and a lot of them are reusing tools that are inside the BCC repository. So Inspector Gadget is kind of relying on the shoulder of BCC to do a lot of things. There are a lot of examples here. Bind Snoop, for example, come from BCC, exec Snoop as well, and so on. There are Snoop tools that are detecting when there is a new exec system call, or Open Snoop, detecting when there is a new open system call to open a new file, and so on. I will show a bit later some example with exec Snoop. So on this BCC tools like exec Snoop and Open Snoop, usually the user experience we want is to trace pods in general. Users don't really care about specific process ID. When we work at the Kubernetes level, we don't want to know about the PID or exactly which node it is running on. We want to use Kubernetes concepts like the pod or Kubernetes labels or namespace and so on. Although when we aggregate information from different processes, from different pods, we want to aggregate them using Kubernetes labels. In summary, we want user experience like kubectl, where developers don't need to SSH on a node and they don't need to know about the internal details about PIDs and so on. So to come up with that, we have this user experience with, for example, the exec Snoop gadget, where we specify which pod to trace using one of those filters. You can filter by Kubernetes labels like this, or using namespace or the pod name or the node, or if you have pods with several containers inside one pod, you can also select which container you want to use. All those labels, you can use one or several of them. You can make combination or just one if you want to. We'll go to next slide. So this kind of filtering is a bit complicated to do because when you use kubectl gadget exec Snoop, for example, there might be 0 or 1 or more pod to trace, and that's how this set of pods to trace change with time, because pod can be created or destroyed over time because it's a dynamic system. And so different tracer can have different pod to trace, and that's change over time. So that's make it difficult to implement. In this example, it uses OC gadget. This OC comes from OpenShift. That's the CLI tool for OpenShift. So if you use OpenShift, you can also use Inspector Gadget as a plugin for OC. If you use kubectl, you can use kubectl gadget as well. Both works the same way. So how does it work? Here, it works with a component that runs in a daemon set called the Gadget Tracer Manager. And this is a daemon running on all nodes, and it has a simple gRPC API with 4 methods. So the methods are to inform the Gadget Tracer Manager of new containers. Every time a new container is started, it knows about it because add container is called. Every time there is a new tracer, exec Snoop, for example, that is started, it knows by this method call. The add container, remove container methods are called by the OCI hooks. So I will explain a bit what is OCI hooks. When you have a Kubernetes cluster, the pods are started by the kubelet through the container runtime. And the container runtime, in the end, for example, execute runc. And runc and other container runtime have this OCI hooks where you can execute arbitrary scripts or commands every time it starts a new container or every time it stops it. Through that mechanism, we execute a command that will call the gRPC method to the gadget tracer manager so that it knows about all the containers on their Kubernetes labels. On the other side, we have a kubectl gadget. When it executes a gadget, it will run it on the gadget pod, and it will use this BCC wrapper shell script that will tell the gadget tracer manager about the tracer, so it knows which kind of node or label or it wants to select. So the gadget tracer manager knows about the container, it knows about the tracer, and can use this information together to know which tracer should trace which pod. The next thing it does, it will update BPF maps with that information. So there is one BPF map for every tracer that will contain the list of pods that need to be traced by this tracer. And if that information changes, it will automatically update the BPF map accordingly. And later, when this BCC wrapper script executes, for example, exec-snoop from the BCC project, it will use a BPF program, in this case, install a kprobe, and it will use the BPF map in order to know whether it should trace this container or not. Okay. So now it's time to share my screen again. So I will go to the next directory. And as usual, there is a README file that you can read on GitHub as well. I will show two things here. The first thing is I will execute this exec-snoop gadget to filter, to get the information on one specific pod. So let me share my screen here. Let's take my screen, sorry. Okay. So here I executed exec-snoop for all the pods in the default namespace with this label. But if I look at that, there is not currently no pods with that label, so it doesn't print anything. Next thing, I will start a new pod with that label. And I will use this command curl something pipe bash, which is maybe a bit of an anti-pattern, but useful for this demo. So I will run in this pod in the interactive board and show what it does here. So first it has to download the Fedora image because I use the Fedora Docker image here. And once it's executed, it runs some script. But at the bottom, thanks to exec-snoop, I can see which command it runs. So mkdir, rpm, rm, and so on. So it has finished to execute it, but exec-snoop captured everything. I can see at the top, execute rpm with this rpm package, and so on. Okay. I can stop that. And the second the second demo I want to show, and this one maybe you can do together at the same time, is deploy Nginx application. So let me show you what it contains. A config map with the files for a website in different languages. And it contains a config map with the configuration for Nginx. So you see Nginx configuration. And then a deployment file, which has 3 replicas of Nginx. and it will use the configuration from that's specified above on the website in the config map that is displayed above. Okay, so let's deploy that. So it creates the config maps, the deployment, and the services. So you can access this Nginx from outside of the Kubernetes cluster through the services. In this case, we use Minikube, so I will use this Minikube service command in order to I use Minikube in this directory. So I use this Minikube command in order to proxy the request through this URL. So if I curl this, hopefully I get something. You can either use Firefox or another browser if you want to. Here I get a 404 error. But then I want to either use this hello.txt file that I put in a config map and hope to get it. Unfortunately, I get a 404 error because there is a bug in my deployment YAML. And here I want to use Inspector Gadget Open Snoop in order to debug that and see what's happening. So I will give 1 minute for you to try that. Okay, so I can continue that, and I will use I will show how to use Inspector Gadget Open Snoop to debug this. So kubectl get pod. Here I see there are three deployments, three pods for my deployment. It means that every time I do a curl command, I'm not quite sure which pod it will reach. But if I do show labels, I see that all of them has this app equal Nginx label. So I can use this filter in Inspector Gadget to filter on the pods with that label. I will use kubectl and Snoop. I will say only the namespace default. And I will say selector on the label app equal Nginx. You can ignore the warning at the beginning and look at the output. Let's see what happens when I do curl. Here I got a 404, and I see that at the same time, I see that Nginx attempted to open this path /etc/nginx/html/hello.txt, and it failed. It returned the error -1, which means it failed to open this file. So that gives a hint what's happening. It attempted to with this file, but we can check if when we install this config map, Nginx data config map, it contains this file, but maybe we mounted it at the wrong place. So that gives a hint. Okay, this config map is mounted in this volume, the nginx-volume. And I see it's mounted in /var/www. But Nginx expected to have it in this path. So that's a mistake. And it doesn't match the configuration of Nginx and where I mounted the volume. So I can use kubectl edit, Nginx deployment, fix that, and find this mount entry and replace that with the correct one. Okay, so now it should hopefully restart the Nginx pods. If I get pod, see that Kubernetes is stopping the old pods and starting new one. And let's see what happens if I do the curl command again. This time I get this good reply. You can see it's getting, I don't get a 404 anymore. Okay, so let me stop the sharing. And we'll go to the next slide and pass the slide to Marga.
All right, so up until now, we've been looking into Inspector Gadget, which was one of the tools that we said we would look into. And now we will look into another one, which is called kubectl-trace. Kubectl-trace is a wrapper around Bpftrace. And Bpftrace is a command that lets you create BPF expressions using a domain-specific language, so that it's easier, so that you don't have to write the C program and compile it and install it. So all of that is done by the BPF tool, and the thing you need to write are the BPF expressions. They are a bit complex, so I'm going to show a few BPF expressions, and you might get a little bit scared, but once you see a few examples, it becomes easier to understand what's going on. So this is what the BPF syntax looks like. This is just the Bpftrace command, and we will talk about kubectl-trace after we understand a little bit what Bpftrace expressions look like. So as this slide is showing, BPF expressions are divided into three parts: the probe, the filter, and the action. The probe is the thing we want to trace. So in this example here, we are saying we want to trace the kernel function called do_nanosleep. So anytime that kernel function is called, our tracer will get activated. The filter, as the name says, it basically allows us to filter the tracing events for some criteria. In this case, the process ID needs to be higher than 100. And the action is what we want to do whenever this probe after the filter gets hit. So this is the most complex part of the syntax. This @ sign with square brackets means that it's creating a hash map, and the key in that hash map called com is basically the command name that was executed. So the command that ended up calling this do_nanosleep kernel function will be there. It could be bash, it could be ls, I don't know, whatever is calling this kernel function in the end, that would be the command. And the ++ is that basically we want to count an increment. And so at the end, when this is finished running, we will have a table with all the commands that were executed and how many times they called do_nanosleep. On the next slide, we will see a couple more one-liners like this. Instead of using the kernel function that we saw in the previous slide, these ones are using trace points. Trace points are points that kernel maintainers and module writers have identified that are good places for debugging. And there's a lot of trace points, and you can use BPF tool to inspect what trace points are available in your kernel. And the good thing about trace points is that they tend to be more stable. There's no guarantee that a kernel function will not change its name or the parameters it takes or the returns values. But trace points are kind of stable. They could still change, but less. And so when there's a trace point for something that you want to trace, it's a good idea to go for that. And in this case, we are both examples are showing syscalls. So this is the trace points for a syscall is starting. In the first example, we are using a similar hash table that is just counting how many times each command executed a different syscall. in the second one, it's using a little bit more complex. It's counting all of the syscalls that were called, regardless of which command called them. And then once per second, it's printing that number and clearing the stack, so that it, in the end, like what will happen is that once per second, it will print how many syscalls were called that second. And so these are just a couple of examples in the website that is pointed there, and it's also in the GitHub repo. There's a lot more examples. There's a huge reference that you can consult. And in our exercises, we will see a few more examples. But of course, like this is super flexible and you can do a lot of things, but you don't need to understand all of it just to start trying some things out. So if you get an idea of what's going on, then you can start using it, and you can like mix and match things from different examples. And so that was Bpftrace. What about kubectl-trace? So kubectl-trace is the way of running Bpftrace commands inside Kubernetes. It doesn't have this handy namespace selection or app label selection. You need to tell it either the node or the pod. And the pod needs to be like the specific pod. No, it can be just like pods that start with this. You have to give it a specific pod for it to run. And you can give it either an inline expression or a file. So if your BPF script turns out to be very complex, you probably don't want to have like a 3-line one-liner. Then it makes sense to have a file where you can add comments and make it a little bit more readable. Okay, and now we will actually see this in action. As we mentioned earlier, it's a good idea to follow along with the GitHub repo because everything is documented there. If you're not sure what we are executing, check out the commands that we documented there. All right, is this still running? I think so, right? Yeah, so let's stop this Nginx deployment. Yeah, and let's now switch to 04. Okay. Yeah. All right. The first thing we will do is create an alias. So the tricky thing about both Inspector Gadget and kubectl-trace is that they need to have access to the kernel headers. And this is why we gave you a Minikube ISO that has the headers, and that why we are using this like special things. It was trying to like simplify getting the headers, because if you don't have the kernel headers, then you can't trace. And so kubectl-trace doesn't have the decompression mechanism to access the kernel headers in our Minikube instance. And that's why we need to give it a different container where it will have this exe executable. And so I'm going to copy and paste. If you are following along, you should copy and paste from the GitHub repo this alias. So what I'm doing here is I'm creating an alias that is called kubectl-trace run that basically calls kubectl-trace run with this long parameters. And then every time I will call kubectl-trace run, it will pass these parameters so that it can access the kernel headers. Okay, so we have the alias. And now what we need to do is know the node name. In our case, the node name is Minikube, but if you're running on a different platform, if you're running inside a VM, it might have a different name. So we need to know the node name where we want to run the expression. And so now I'm going to copy and paste this expression. So what I'm saying here is I want to run this trace in my node called Minikube, and it's going to be a syscall trace. And what I'm doing here, it's a little bit different than the one I showed in the slides. What it's doing is it's tracing all the syscalls, and then it's creating a hash table with the probe, which means the syscall, as the entry. And then it's counting how many times it's called. Okay, so we're going to create a hash table that has all the syscalls that were called and how many times those syscalls were called. Oh, sorry, I forgot to actually install kubectl trace. So here there's this get kubectl trace script, which looks very much like the inspector gadget script that will install the plugin for me. Of course, you can install it yourself. This is just a handy way to save time. And it's installing. Yep, now it's done. Now let's try the other command again. Okay, so it says that it created a trace, and we can actually list whichever traces it has. Right now, it will have only one trace. But as we try things out, this list will get longer with all the different traces that kubectl trace is collecting. And to actually interact with the trace, we will attach to it. I will copy and paste this one. I could also copy and paste this one, but it's annoying because it's mixed together with the node name. So, okay. I'm attached to the trace, and now the kind of trace that I executed only prints something at the end. So in order for me to see anything, I need to tell it to finish, and then it will print something. So I will press Ctrl Z, and okay, so if this happens, it means it didn't work. If it says signal killed, it means that it got killed before it managed to print the table, and we need to try again. So I'm going to try again. So this is the trace I want to run. It says it's created. And now I want to attach to it. And now I'm going to press Ctrl C again. And this time it printed the table. I'm not sure what the other thing is, clearly a bug, but I'm not sure what the bug is. Let's not worry about that right now. Anyway, it printed a table. We see that there's a bunch of different syscalls that are being called. We see, yeah, a lot of different syscalls. I'm interested in the write syscall, like what is being written. Like I stopped everything. There's nothing really going on in my cluster. So why is anybody writing anything? So I want to see why there's a write call. So for that, I will edit my previous trace, and instead of having a star here, I will check the write syscall, and instead of counting per probe, because this will only be write, I will count per command. So I will see which commands are writing. And to avoid this having to like start the trace and then attach myself, I'll use the -- attach command. And this will just let me stay attached when I run it. So now the trace is created. It attached one probe to the kernel. So it's now gathering data of which programs are writing stuff. And I will now stop it, and it should print a table. Yeah. So we have a table of a bunch of different things that we're printing. Kubelet writing. Kubelet is the one that's writing the most. etcd is also writing a lot. And yeah, we could inspect why any of those are writing, but I mean, yeah, they are writing stuff. But let's check, for example, out of those, let's check one of them. So to check one of them, remember I said that there was this filter part. Like up to now, the examples I showed had no filter. So now I would add a filter. And in the filter, I will say I want to check if the command is core DNS. So if the command is core DNS, then this will match. And now I don't want to count stuff. I know that it's writing and then it's core DNS. So what will I count? What I wanted to actually see, what is it writing? So to do that, I will do a printf. And then to the printf, I'm going to pass the arguments of the trace point. And from the arguments, I'm going to select the buffer. So with this, what this will do is it will print every time core DNS writes anything, it will print what it is that it's writing. Okay, and so we see that it's responding to HTTP requests, and to most of these requests, it responds 404 not found. So there is some service, probably a liveness check that is trying to check if it's working, and it's responding 404 not found, which is kind of interesting. But anyway, we see that this is what core DNS was writing. All right, so that was like the basic usage of kubectl trace. We are now moving on to the next example, which will use one of the files that we have here, the bash readline. So in this bash readline file, we have a script. And as I mentioned, because it's longer, we have comments and we can format it so that it's easier to read. And so this is an example that traces bash commands. And here what we see is that it has this special variable called container PID that is replaced eventually after a few calls. It gets replaced by kubectl trace for the PID of the container that is executing this the probe that we want to match. Why does it need to get replaced? Because here the trace that we are using, the probe, is called uRedProbe. It's a user space function. And so it needs to access the executable, the bash executable that we are going to trace here. It needs to actually access the file. And to access the file, it needs to have the right inode and to be able to find the symbol for the readline function. And so that's why we have to put this container PID here, and then kubectl trace will replace it. Okay, let's see it in action. We are closely running out of time, so I need to hurry up a little bit. So the first thing I'll do is I'll split the screen, and in this side of the screen, I'm going to start a test pod that will just have a bash command in it with an Ubuntu image. Yeah, okay, and it's working. I have an Ubuntu image and I have a bash command in it. And now on the other pod, the other part of the screen, I'm going to attach to that pod and execute the bash readline. So like this. So I'm going to do a kubectl trace run, and I'm going to pass the file that I showed. And then instead of the node, like I showed before, I'm going to attach to the pod and keep it running. So my trace is created, it's waiting for tracing bash command. And then on the other side of the screen, I will try things. Whatever I type here will get printed. So, and even if I type a command that doesn't exist, it will get printed, because this is basically what we're doing. We're tracing what the readline function returns. Okay, you might ask yourself, okay, this doesn't seem particularly useful. Why would I want to trace what bash commands are getting executed? Maybe it's useful for someone trying to hack my system, but not for me to debug anything. So let's now actually debug, or well, see how we would debug in an actual Kubernetes application. So for that, I will stop this trace. And one of the other things that we have in this directory is this Catterday YAML that has a deployment of a Catterday application. And I will apply this Catterday YAML. Okay, it applied. And now this is an application that serves a website with cats in it. And so I will, in order to use it, I need to use a Minikube service redirection. So I